Hello everyone, this is Anusha Rai from Namchi Government College, BSc Physics 6th semester, and I've prepared a presentation with help and support of our respected HOD Dr. C.P. Khatiwara on the topic of Schrodinger wave equation for hydrogen atom. So before moving on with our topic, I would like to give you a brief description on what is Schrodinger equation. So the Schrodinger equation is a linear partial differential equation that describes the wave function or state function of a quantum mechanical system. Its discovery was a significant landmark in the subject of quantum mechanics. So it was derived by Erwin Schrodinger in the year of 1925, and he published it in 1926, and he got the Nobel Prize for the same in 1933. So basically it's one of the application of Schrodinger time independent wave equation, and as we all know that hydrogen atom, it has a single electron, and this electron is trapped in the field of the positive proton or nucleus. Since electron it's a negatively charged particle and is bound by the potential of the positive nucleus, so here on solving this equation we also include the potential energy of the electron, which is given by Vr equals to minus of E square by 4 pi epsilon naught r. So let us see when we solve the time independent Schrodinger equation for hydrogen atom, and we also include the potential energy of the electron, what new information do we get? So for solving this equation, first of all, we write the Schrodinger time independent equation, and that is delta square of psi plus 8 pi square m by h square a minus v psi equals to 0. When we write the same equation in terms of x, y and z coordinates, what we get is partial square of psi by partial x square plus partial square of psi by partial y square plus partial square of psi by partial z square plus 8 pi square m by h square e minus v psi equals to 0. Now, as you can see here from the diagram that hydrogen atom is a spherical system, whereas the equation that we have written, it's in Cartesian coordinates. And also the electron which is orbiting around the nucleus, it has its angular momentum, that is it makes some angle with the nucleus. So this angular momentum, it cannot be explained by Cartesian coordinates. So first what we need to do is we transform the Cartesian coordinates into spherical polar coordinates. So what are spherical polar coordinates? They are r, theta and phi, where theta is the polar angle, whereas r the radius vector and phi the azimuth angle. So before that, let us see how the rectangular coordinates are related to the spherical ones. So x equals to r sine theta cos phi, y equals to r sine theta sine phi, z equals to r cos theta. This you can write from the symmetry given in the diagram. So the spherical polar coordinates r, theta and phi of the point P have the following interpretations. That is r, which is the length of the radius vector, theta, that is the angle between radius vector and z-axis, and phi, which is the angle between the projection of the radius vector OP on the xy plane and the positive x-axis. So now, as we already discussed that we need to convert the Cartesian coordinates into spherical ones, but how do we do that? Okay, so if you recall from what you have studied earlier in mathematical physics, each of the second derivatives that exist in the above equation that is the Schrodinger time independent equation which we have written earlier, okay, each of the second derivatives which exist in that equation is related to the spherical ones by del square psi by del x square equals to 1 by r square del by del r square del psi by del r, del square psi by del y square equals to 1 by r square sine theta partial by partial theta sine theta partial psi by partial theta, and del square psi by del z square equals to 1 by r square sine square theta partial square psi by partial theta square. So now when you substitute these values in the above equation, what do you get is 1 by r square partial by partial r square partial psi by partial r plus 1 by r square sine theta partial by partial theta sine theta partial psi by partial theta plus 1 by r square sine square theta partial square psi by partial phi square plus 8 pi square m by h square e minus v psi equals 0. Here we did nothing, we simply substituted these values in the above written Schrodinger time independent equation. Okay, so in the same equation, when we put the value for potential energy and also divide the equation throughout by r square sine square theta, what we get is sine square theta partial by partial r square partial psi by partial r plus sine theta partial by partial theta sine theta partial psi by partial theta plus partial square psi by partial phi square plus 8 pi square mr square sine square theta by h square e plus e square by 4 pi epsilon naught r psi equals to 0. So mm, so as you see in this equation 3, this equation consists of three variables that are theta, r and phi. So in order to solve this kind of equation, we use the technique of separation of variables. So what is separation of variables is if a function consists of a function more than one variable. So let us denote that function by psi. So according to the theory of differential equation, we can write psi of r theta and phi equals to psi 1 r, psi 2 theta and psi 3 phi, where psi 1 is a function of r alone, psi 2 is a function of theta, and psi 3 it is a function of phi alone. So in the next step, we partially differentiate psi with respect to r, theta and phi. So why we are doing this is we will substitute these values in equation number 3. So when we partially differentiate psi with respect to r, what we get is del psi by partial r equals to psi 2 psi 3 del psi 1 by del r. So psi 2 and psi 3, since it's a function of theta and phi, and here we are differentiating with respect to r, so psi 2 and psi 3 will be treated as constant and only psi 1 will be differentiated. So since a function having a particular variable r, that is psi 1, is differentiated, so we can write it as d by dr and not del by del r. So similarly, partial psi by partial theta equals to psi 1 psi 3 del psi 2 by del theta, and partial square psi by partial phi square equals to psi 1 psi 2 d square psi 3 by d phi square. So when you substitute these values in equation number 3, what you get is sine square theta partial by partial r square psi 2 psi 3 del psi 1 by del r plus sine theta partial by partial theta sine theta psi 1 psi 3 del psi 2 by del theta plus psi 1 psi 2 del square psi 3 by del phi square plus 8 pi square m by h square r square sine square theta e square by 4 pi epsilon naught r plus e psi equals 0. Okay, so when you rearrange this equation, you get psi 2 psi 3 sine square theta partial by partial r square del psi 1 by del r plus psi 1 psi 3 sine theta partial by partial theta sine theta del psi 2 by del theta plus psi 1 psi 2 del square psi 3 by del phi square plus 8 pi square m by h square r square sine square theta e square by 4 pi epsilon naught r plus e psi equals 0. So when you divide this equation throughout by psi 1, psi 2, psi 3 and rearrange the equation, we get sine square theta by psi 1 del by del r square del psi 1 by del r plus sine theta by psi 2 del by del theta sine theta del psi 2 by del theta plus 8 pi square m square sine square theta by h square e plus e square by 4 pi epsilon naught r equals to minus 1 by psi 3 del square psi 3 by del phi square. So see, in this equation, the left hand side of the equation is a function of theta alone, whereas the right hand side of the function is a function of phi alone. So, and it's given that left hand side of the equation it equals to right hand side. So the only possibility that the left hand side of the equation must be equal to the right hand side is when these two equations equals to a same constant. Let us denote that constant by m square L. So therefore the differential equation of function psi 3 is minus 1 by psi 3 del square psi 3 by del phi square equals to m square L, which gives the azimuthal equation. So on rearranging this equation, we get del square psi 3 by del phi square plus m square L psi 3 equals to 0, where m square L is called magnetic quantum number, which we'll discuss in next video. So again, when we substitute m square L for right hand side of the equation 5, divide the entire equation by sine square theta and rearrange, what we get 1 by psi 1 del by del r square del psi 1 by del r plus 8 pi square m r square by h square e plus e square by 4 pi epsilon naught r equals to m square L by sine square theta minus 1 by psi 2 sine theta del by del theta sine theta del psi 2 by del theta. So again, in this equation, what you see is the left hand side is a function of r, whereas the right hand side of the equation is a function of theta. So again, what you do is we shall require the both sides to be equal to a similar constant, and we call that constant as L plus 1. So therefore the equation for the function psi 2 and psi 1 are m square L by sine square theta equal minus 1 by psi 2 sine theta del by del theta sine theta del psi 2 by del theta equals to L plus 1, which is the polar equation, and 1 by psi 1 del by del r square del psi 1 by del r plus 8 pi square mr square by h square e plus e square by 4 pi epsilon naught r equals to L plus 1, which is the radial equation. So in the next video we'll be dealing with the solution of these three equations, that is the azimuthal equation, the polar equation, and the radial equation. So thank you for watching.